All right. So, lesson 2.7, polynomial and rational inequalities. But before we get into those, kick off, find the slant asymptote of f of x equals x squared minus 4x minus 5 over x minus 3. So, if we think back to asymptotes, vertical asymptote was what makes the bottom be 0. Well, in this case, the vertical asymptote would be at 3 because 3 minus 3 is 0. So, x equals 3 would be the vertical asymptote. Horizontal asymptote is when we're looking at these first exponents, biggest terms here. So when the exponent on top is smaller than what the exponent is on the bottom, then that's when we have a horizontal asymptote of y equals 0. When they both have the same exponent, well, then it's the coefficients in front. And so it'd be like, say, if it's 4x squared over 2x squared, it'd be 4 over 2, which is 2. So y equals 2 would be the horizontal asymptote. When the top is bigger like this, that is when we don't have a horizontal asymptote, but that's when we're going to have a slant. And to find the slant, we take the top divided by the bottom. Now we can do this long division, or we can do the synthetic a little bit easier, so let's go that route. So in the box will be opposite sign, so it'd be a 3. On top, we put exactly what we got, so 1, -4, -5. Draw our line. So we bring the 1 down. 1 times 3 gives us 3. So 3 and -4 would be a -1. -1 times 3 would be a -3, and we get -8. Now, first number, we put the little line to separate it. That's going to be a remainder. We don't worry about the remainder with our slant asymptote. We're worried about these two, the quotient, which remember, this is the constant, this is the x term, so our slant asymptote would be y equals x minus 1. The x and the minus 1. Okay? So that's how we get our slant asymptote. Moving on from there. Polynomial inequality. Basically, it's polynomial, that's an inequality, right? So inequalities when we have the greater than, less than, greater than or equal to, less than or equal to symbol, but we're dealing with polynomial. So we have variables, numbers all put together, not just a simple x is greater than 2, but like x squared, x cubed, stuff like that. Now, when we do this, we have a big long checklist here of things that we can talk about, of how we go about it. Basically, what we're going to do is this. Now, first off, we need to get everything, every term on the same side and the other side be 0. Whether it's greater than, less than, greater than or equal to, less than or equal to, just have all the terms on one side, 0 on the other. Then we're going to solve it for when x equals 0. So we'll set equals 0, solve it out for our x's. Those x's are going to be our boundary points, which is what's going to break up our domain. Now, typically our domain is going to be -infinity to infinity. Especially with the polynomial side, there's going to be no denominator, so there's nothing to make it not equal 0. Nothing to make it equal 0, sorry. So there's nothing that we need to exclude. Then we're going to break that into intervals, that domain, with those boundary points, and we're going to take a test value from each of those intervals. And we're going to put it into our equation. We're going to solve that out, and we're looking for whether it's positive or negative. If we want to be greater than 0, we're looking for the positive numbers. If we want to be less than 0, we're going to look for the negative numbers. And that's what's going to lead to our solution set. Now, the intervals that work will be our solution set, and then we'll graph it on our number line. So keep in mind, yes, it works for any of all of these. Keep in mind, closed circle if it's the bar underneath. So closed circle, or in other words, bracket. If it's just these, we're going to have the parenthesis or the open circle. Okay. So let's do one. So we're going to graph the solution set on a real number line of 2x squared plus x greater than 15. So first thing we got to do is we got to move this 15 over, and so we would have 2x squared plus x minus 15 being greater than 0. So from here we're going to solve. So our 2x squared plus x minus 15 equal to 0. We're going to factor this. And so it's going to factor out to be 2x minus 5 and x plus 3. So each of these would get an equal 0. So we add the 5 over and have 2x equaling 5. And we divide the 2 over to have x equals 5 halves. Here we just subtract the 3 over and have x equals negative 3. So these are going to be our boundary points. So what we're going to do is we're going to draw 2 lines. So negative 3 is the smaller number, and 5/2 the bigger number. So again, nothing on the bottom. So our domain, negative infinity to infinity, so all reals. So that's what's going to get broken up. Negative infinity until our first boundary here of negative 3. Then we go from negative 3 to 5/2. And then we're going to go from 5/2 to infinity. So test value from each one. So a value that fits each one. So I'm going to go negative 4 here. I'm going to do 0 here, and I'm going to do 3 on this one. Okay. So what I'm going to do now is I'm going to get out a graphing calculator. So makes this so much easier. So if I turn this on and I'm on my regular screen, let's slide this up a little bit. So y equals is where we're going to go. Now, if there's anything in here, we just hit clear that out. Next, we're going to put in this equation right here. So where we have it set equal to 0 before we factor it, that's the equation you're going to put in. So 2x squared plus x minus 15 is our equation. So then we're going to hit second graph to go to our table. And again, if there's stuff here, delete it out of the way. Don't hit clear, because I'll just clear the spot, and then you still got to arrow around and delete stuff. Hit delete, it'll get rid of it. So we have our test values, and that's what we're going to put in. So negative 4, 0, and 3. So we're looking at these. We have a positive, a negative, a positive. So we would get a positive here, a negative, and then a positive. Okay. So looking back over here at our original thing, we want to be greater than 0. Well, greater than 0 means positive, so we want the positives. The negatives won't work. So in this case, we're going to have from negative infinity to negative 3, unioned with 5/2 to infinity. Now, we're just greater than, so we don't need the brackets. We don't have the equal to part. So when we go to graph this, then we'll use open circles. So we have a spot here at negative 3, spot here at 5/2. And if we're from negative infinity to negative 3, we're shading this way with an open circle. Open circle shading this way because we're 5/2 to infinity. So we're bigger than that, less than that. So first one's done. That's kind of how this is going to roll. So let's do another one. So now we're going to graph the solution set on a real number line of x to the third plus x squared is less than or equal to 4x plus 4. So again, everything's got to go to the same side. So because we have the x squared, x cubed on this side, we're going to move these over. So we will have x to the third plus x squared. We'd subtract the 4x over and subtract the 4 to be less than or equal to 0. So if we have this set equal to 0 now, and we would solve. So 4 terms, we're going to look for grouping, see if that'll work. So the first ones, we can pull an x squared out, and we would have x plus 1 left. The second set, we would pull a negative 4 out and have x plus 1 left. So when we group these together, our x squared and minus 4 go into 1. Other parenthesis is what's in parentheses already. Now, before you break this up, look for, can I break it down even further? I should say that differently. Before I set it equal to 0 and solve, look to see if you can break it up more. So x plus 2, x minus 2, because this is a difference of squares, and then x plus 1 equals 0. So if we set each of these equal to 0 and we solved, we would get x equals negative 2, negative 1, and 2. So we'd subtract the 2 over, add the 2 over, subtract the 1 over. So we're going to have 3 boundary points this time. So 1, 2, 3. So again, we're breaking this up from negative infinity. Oh, I should put my boundary points in. So negative 2, negative 1, and 2. So negative infinity until -2, -2 to -1, -1 to 2, and then 2 to infinity. So first one, test value, I'm going to do -3. Here, -1.5. I'm going to do 0 and 3. So again, come to your graphing calculator. We're going to delete these out. And I'm going to go back to my y equals, and I'm going to clear this out. So put in the new deal. Again, I'm doing it here where we're equal to 0. Now, we're not going to worry about the parentheses for right now because that was part of the grouping part. So what we're going to have is x, and we're going to need the little caret button here to the third. So we can put that in. Arrow to the right here to get out of the exponent, plus x squared minus 4x minus 4. So we're there. Go second graph to get to our table, and we can put these in. So -3, enter. -1.5, enter. 0, enter. 3, enter. So as we look at those, we are a negative, then a positive, negative, then a positive. So you might have noticed from the last one and this one, we have a pattern of opposites. That should how it be. That's how it should be. Wow, can't talk. That's how it should be. It should alternate here. If you get the same signs, then check your boundary points because it should switch at the boundaries. So if we go back to here, we're looking for the less than or equal to 0. So the negatives, so the first one's good, second one don't need, third one's good, last one don't need. So if we wrote this, -infinity to -2, union with -1 to -2. Now, this would be good and grand if this was just less than, but because it's equal to, the numbers should have brackets. So we're going to change this. Now, -infinity, infinities always have parentheses, but the -2 will have a bracket unioned with a bracket, -1, comma, negative, or +2, should be a +2, bracket. So when we do our number line, we have one at -2, -1, and at 2. So close circle at -2, close circle at -1, close circle at 2. We're going from -infinity to -2, so we're shading this way. Nothing in between, but then from -1 to -2 works, so we shade in between there. So it's kind of like the and/ors that you've seen in the past, working with inequalities, but they're a little bit different because the polynomials are a little bigger. There's more than just maybe 2 solutions. There could be multiple solutions. Okay. Or there could just be one. Now, we're going to shift gears a little bit, and we're going to go to rational inequalities. So rationals mean fractions. So the inequalities, like the one down there, like this one, that have a polynomial over a polynomial. Most of the steps are going to be the same. We're still going to get all the terms on one side with 0 on the other. But the only difference is like here, if we have this 2 and we subtract it over, we have to get it over that denominator. So the numerator takes up the entire top, the denominator takes up the entire bottom. We don't have a plus or minus something with it. It has to be one fraction on that side. Then we're going to take the numerator, set it equal to 0, and solve. We're going to take the denominator, set it equal, and solve. And what we get out of those two will be our boundary points. What x equals will be our boundary points. Separate them, the intervals, which again should still be fairly -infinity to infinity, because by setting the bottom equal to 0 and solving, we're finding what x equals 0. And so those are going to be boundary points. So that'll take care of that. So let's do this one. So we'd subtract the 2 over, like I said already. So we'd have x plus 1 over x plus 3 minus 2 being greater than or equal to 0. Now, before we can add or subtract fractions, we have to have a common denominator. So common denominator in this case would be x plus 3. If we times the bottom by it, we have to times the top by it. So if we put this together, we'd have x plus 1. We'll have to distribute the minus 2 in. Have a minus 2x minus 6 over x plus 3, which again is greater than or equal to 0. And then we can put like terms together. X and minus 2x would be a minus x. 1 and negative 6 would be a minus 5 over x plus 3, greater than or equal to 0 again. Okay. So we have it all as one fraction on the left side. So now we can take our top, negative x minus 5 equal 0. We'll set equal 0 and we'll solve. So we can add the x over and get x equals negative 5. Then we're going to take the denominator, x plus 3, set it equal to 0. So we'd subtract the 3 over, and so x would equal negative 3. So those are going to be my boundary points. So negative 3, oh, I should do negative 5, and negative 3. Should do numerical order. Still going to break up from negative infinity, negative 5 to negative 3, and negative 3 to infinity. So test values, I'm going to go negative 6, can't do 0, negative 4, get ahead of myself, and 0. So again, calculator comes in handy. Going to delete these out, go back to my y equals, and clear that out. So I'm going to put this in here, but when we do it, we have to put the entire top in a set of parentheses. So parentheses, negative x minus 5, close the parentheses. So the entire top has to be in a set of parentheses, and we divide and put the entire bottom in a set of parentheses. X plus 3. So then we can go second table, go to our graph here. We're going to put in those test values of negative 6, negative 4, and 0. So we go negative, positive, negative with our numbers. So negative, positive, negative. Now, if we go up here just a little bit, we want to be greater than or equal to 0. So we're looking for the positives. So this one's out, this one's out. So negative 5 to negative 3. Now again, we were greater than or equal to, so we're going to need brackets. So a bracket over negative 5 comma negative 3. However, negative 3 is what made the bottom be 0. So that still would be something we would exclude from the domain. So it's not a point we would include in this, which makes it a parenthesis. So when we do our number line, we'd have a closed circle here at negative 5, open circle here at negative 3. But we're going to shade in between. So one extra step in this is, even though we're looking for, because this is greater than or equal to, we need the brackets, we have to keep in mind with our rationals what makes the bottom be 0, because that we still have to exclude. So if we put a negative 3 in here, negative 3 and 3 makes 0. So negative 3 is excluded from the domain, which means it can't be a solution. So it stays a parenthesis and it's an open circle. All right. Now, for as far as the position of a free-falling object near Earth's surface goes, it's going to be in this sort of a formula of S of t, which stands for position, equals negative 16t squared, t is time, plus v naught. V naught is your initial velocity times t time, plus s naught, which is your initial position, which is what this second paragraph here all explains, is what's what there. So we're going to use that equation with this here. So we have a ball thrown vertically upward from the top of the leaning tower of Pisa, 190 feet high. And no, it is not pizza that you eat, it's pizza. Yeah, bad joke. It's okay. With an initial velocity of 96 feet per second, so initial velocity there, at which time is the period of the ball's height exceeded that of the tower. So if we set up our function here, we have S of t equals negative 16t squared plus v naught initial velocity. Well, it said initial velocity is 96 feet per second, so 96t plus s naught, which is our initial height. Well, if we're throwing it from the top of the tower, which is 190 feet high, that's our initial height. So plus 190. Now, we want to be exceed the height of the tower. So taller than the height of the tower, we're going to be bigger than the height of the tower. So greater than. And since we're exceeding, we're going to say just greater than, not equal to, because that's when we're the same, not exceeding. But the height of the tower is 190, so we have to be bigger than that. So, again, we're going to solve these like we've been solving. So get all the terms on one side, 0 on the other. So we'd subtract the 190 over, and so when we do that, this cancels out over here. And so we're left with negative 16t squared plus 96t greater than 0. So if we factor that, we could pull a negative 16t out. And so we would have t plus, there are 6 16s that go into 96. And this should be a minus if we're pulling the minus out, sorry. But minus 6. Greater than or equal to 0, which we're actually going to say just equal to 0, sorry. Because we're going to solve this. So we'd have negative 16t equals 0 and t minus 6 equals 0. So if we divide by negative 16, we still have t equals 0. And if we add the 6 over, we have t equals 6. So these are our boundary points. This is what we're going to break this up by. So 0, 6. So negative infinity to 0. 0 to 6. And then 6 to infinity. Now, if we think about this, before we throw the ball, would it necessarily be above the tower? No, it really wouldn't. So we don't even have to look at this one, really. We can't be above the tower before we throw it. So we just got to look at 2 of these. If I put my parentheses on. So between 0 and 6, I'm going to pick the middle and go 3. Bigger than 6, let's go 10. Nice numbers. So we're going to put this back into here. Again, delete what's already there. Go into your y equals. Clear out what's in that y equals. So this is what I'm going to put in. So once you get it solved for 0, that's always the equation you're putting in here. So negative 16, and we're going to use x, xt, it's just a variable, but x squared plus 96x. Again, x going in for the t. So second graph, going here. I'm going to put my boundaries, or my test values, sorry, of 3 and 10. So I'm positive here, negative here. Now we want to be greater, so we're looking for the positive, so we don't want the negative. So we're going to go from 0 to 6, parentheses. Again, we're greater than, so we're going to stay parentheses. So on a number line, we have our 0, we'd have our 6. We're both open circles, shading in between them. And that's it for this lesson. So, have any questions, let me know. Pan me, email me, send me a message on Google Classroom. Any of those work. Otherwise, until next time, we'll talk to you later.